coder. Coffee stains and name chains, I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over. LeetCode, beast mode, 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 LeetCode, beast mode. This is not a main thing, really I'm a coder. Coffee stains and name chains, I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over. LeetCode, beast mode, 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 LeetCode, beast mode.
LeetCode, Beast Mode, what's up, chat? We out here. Got a coaching session with Sean. Gonna hop in the call real quick. Let's get active. I couldn't get that last question, unfortunately. I think it was decent. The first 2 questions kind of easy. Then what I rank, see if my rating goes up. I haven't been doing as much contest as I would like, but I'm gonna get back into it. Like I didn't really LeetCode too much in the last February, March, and April. January is when I tweaked out. I need to keep that same velocity. See if I can bring up a coder pad. Perfect. I might need to pay for coder pad or build my own. Or also there's like this collab feature. Shaw, what's up, man? How you
What's
doing?
up? Wait,
How's your day? Can you hear me?
Yeah, let me see if I can get headphones. Give me a sec.
Okay, let me get you up on the screen while you're at it.
Are you getting reverb when you talk? Because I'm charging my headphones.
No, I'm good.
Okay.
You're good. One sec. Let me just get you up on my screen. Are you live too?
Am I live? No, I'm not live.
Yeah, I saw you doing like some hard ass DP question. Not DP. I don't know what it was. Actually, yeah, like some hard code forces questions.
Yeah, I was doing something called centroid decomposition, which it sounds more complicated than it is.
What is it?
It's like a centroid you can kind of think of as the middle of a tree. And so the middle of a tree is basically the point that you cut it, and then all the other pieces, the remaining pieces, are kind of the same size. And so if you can locate the centroid of the tree and basically split it into these equally sized pieces, you can, and you repeat that process over and over, you can do things in n log n time, which would normally take more time.
I see. Chat, how's the audio? One sec, let me verify. Did you end up doing the contest? Like, how did that
I
go
did.
for you? Nice.
It was rough. It was probably my worst rank in over a year.
Oh, really? What happened?
Yeah.
Was that one harder? Or...
I thought that was the hardest fourth question we have had in a very long
Oh, no
time.
way.
Besides maybe one recently.
Interesting.
Yeah, I don't think the solve count really reflects how difficult the problem was.
Yeah. Here,
A lot of
I
strong
didn't
solvers.
solve it, but I didn't know if it was that hard because I kind of like thought of ideas. Sometimes it goes way over my head, but I get
Mhm.
like, but I didn't really come up with a solution.
Yeah, I also didn't solve it.
Do you know how to solve it now?
I do.
Okay. Let's walk through it then.
Yeah.
Maybe we can do. How are we gonna do this? Let's go to that last question. I feel like there's a LeetCode feature where you can just share a question. You could hop on at the same time.
Oh, is there?
Oh yeah, invite. I'll send you an invite link.
Okay, yeah, that might be useful. But I actually think something that's a little bit more instructive is to go over a simpler problem first.
Yeah, I'm down.
Are you familiar with what a segment tree is?
I've worked with binary index trees, so I kind of know what it is. It's like like if you're trying to do prefix sums or range queries really fast,
Right.
you can run that.
Yeah. So I think what's more useful than just going through this problem and explaining how to solve this problem, my concern with doing that is it's better to teach like a repeatable framework, how to break down problems, how to solve problems. And so I think we should start at a simpler question and understand the principles behind that, and then see how we can apply that to this.
I'm down.
But to understand the simpler version, we need to understand a segment tree. So I feel like we could do a quick crash course of a segment tree first, and then we can do the longest increasing subsequence problem, not this one, a different one, just the basic longest increasing subsequence problem with a segment tree. And then we can see how to apply that to this question. I feel like that would be the most instructive.
That makes sense. I invited you to a coder pad as well, so like if you want a whiteboard or anything.
Let me do that. That'd be
Yeah,
great.
I sent it to you on Google Chat.
Okay.
That's a good idea. Instead of hopping this, let's work on because I honestly built this binary index tree once.
Right.
Not really built a.
Okay. I am on the whiteboard. If you can see it, if I draw, you might want to put it on the
Yeah, I could
on
see
your
it.
stream. Also, maybe my stream is behind because I can only see the code part, not the whiteboard.
You can't see the whiteboard.
Not on your screen. Oh, maybe my screen is behind. Sorry, 1 sec. Okay, as long as you can see it, that's fine.
Like the stream?
See it.
Yeah. They
Okay.
can see it.
Okay. So let's talk about the segment tree. So basically, we have an array of some numbers, and I'm just gonna happen to write these numbers that are the indices as well. So like just to keep it simple. So we have 0, 1, 2, 3, 4, 5 in an array.
Yeah.
We need to support operations to, let's say, get the maximum in some range, which in this case is 4, and then also update an element. So maybe make this 2 into a 10. That's one basic use case that a segment tree can do. A segment tree can do a lot of things. It can find the maximum in a range. It can find the sum. It can overwrite elements like we saw. It can add to an element. So instead of overwriting it, we can just say add 3 to this element. It can do a lot of things, but it essentially does range queries quickly and point updates. So something that updates a point. There's more complex applications which can do range updates. So maybe we overwrite all of these, but we're not going to work on that. That's called a lazy segment tree. So yeah, range query. So ask a question about a range and then point update.
Okay. And then like we obviously can't just do a regular prefix sum because once you update a specific point, you just have to update everything to the right, essentially. Right?
Exactly. So the naive way is we just store a list of the elements, and then every time we do a point update, we literally just in O of 1, we update that element. And maybe that's good if we have very few queries. But every time we have a query now, we have to like walk this. If this is the query range, we have to spend that much time, right? Just looping over and getting the sum. So that's slow if we have a lot of queries, right? There's other ways to do this type of thing. This is kind of the gold standard. So we're going to go with this. Okay, so what is the structure of a segment tree? I'm scrolling down here a little bit. We're going to have a node at the top. And this node, let's say our array is 10 indices long, or it goes from indices 0 to 10. So I guess that's 11 indices. So this first node at the top of our tree is going to hold some data. And it's going to hold data relevant to this entire index range, right? Okay. We don't know what the data is yet, but it's going to hold some data. And that node is going to have 2 children. It's going to have a left and a right child. The left child holds data about the left half of that range. So maybe like 0 to 4 or something, 0 to 5, we'll say, right? And the right child is going to hold data for the right half. And again, we don't care about what this data is yet. So this is a recursive procedure, and it's going to go, I'll just draw a few more. It's going to go all the way down until at some point, you know, we get to a base case. We get to a leaf node, which holds data about like a single index, right? So again, this range that I'm drawing, this corresponds to part of the array. This root node holds data corresponding to the whole array. The first left child holds data corresponding to the first half of the array, and so on. So my first question is,
that makes sense.
How many nodes are in this tree? Well, we can see what is the height of the tree. Like if we call the array size n,
log n essentially,
right? It's log n, right? Because each time we drop, we're halving the range, right?
Mm-hmm.
Halving the size, and you can only half the size log n times. So the height is log n, and it might look like there is n log n nodes here, but there is actually going to be n nodes in total. And you can see that because the bottom layer has exactly n nodes, because it's going to have 1 node per index. And so we have n nodes. The layer above it has n over 2 nodes. The layer above that has n over 4 nodes, and so on. And that sums to like 2n, right? It's a geometric series. Okay, yeah. So we have n nodes. And so all of these nodes are going to take up memory. And so that means we're going to take up n memory in the tree to build this out, right? So O of n space. Okay, let's talk about what the data actually is. It kind of depends on what we're querying. Let's say we want to know the maximum in some range. So the max in this index range from 0 to 10, this root node, and let's just say the array is like 0, 1, 2, all the way to 10. So obviously the max of the entire array is a 10. So instead of having a question mark here, we're going to say the data stored at this node is the max if we want to store the max. Same thing here on the left child. What is this data point? Well, the max in that range is going to be a 5. max in this right one is going to be a 10, and so on. So we build all these nodes. Now we want to do two things. We want to update a node. We want to overwrite some index, right? Because that's the initial problem. I want to be able to cross out this 3 and say this is now a 15.
Yep.
How does that work mechanically in terms of our tree? What's going to happen is we're going to start at the root and we're going to walk down looking for that 3, right? Looking for the index 3. So index 3 lives in the left child here, right? We're at the root and we're saying we need to go find this 3. So I'm going to say jump left. Still exists. So let's say this range here is 0 to 2.
When we say update, we're updating a specific index, right? Or okay,
We're
we're
updating in this array. We're just changing the value at some exact index, right? Let's say this is 3 to 5. So we started at this root. We're going to find that like leaf node. We jump left. We look over here and we say, okay, 3 is not in this left range anymore. So we're gonna jump right. Can I not Control Z? We're gonna jump right. And then we're gonna keep jumping until we locate that leaf node. How long does this jumping process take to go find that leaf node?
like log n to get.
It takes log n, right? Because again, the height of the tree is log n. So we're going to walk down log n nodes. And then what are we going to do when we get here? What was previously stored at this 3 was a 3, right? But we just said we're overwriting it with a 15. So
yeah,
what happens? We edit that node's data, right? We're at this leaf node. We're going to say this is now 15.
Yep.
And now this node is correct, but all of these previous nodes that contain a 3 are incorrect, right? Because what did this 3 to 5 range say? It said the max was a 5. That's no longer true. The max is 15. Or for instance, this root node, it says the max is 10. That's no longer true. It's 15. So we then have to bubble up from we're going to use recursion. So we're going to bubble up from the recursion and we're going to repair all of the nodes.
I see.
Right?
That makes sense.
Okay. So that is how update works.
Like,
and
we have to do it bottom up and not top down, because like bottom up, like we know for sure when we update that value that value is going to change. But when we go up to the other range, it might not actually change. Like 3 to 5, it might not actually be the max there, like that new number you said.
Are you asking in terms of the implementation? How does it work? Or
like, why do we have to bubble up the max value from the bottom up instead of just go when you're doing the recursion from the top down, just set everything to 15? But it
yeah, that's a good question. Maybe in this specific case we could do that, but I'll give you a slightly more complex example. Let's say these nodes were not storing maxes; they were storing sums of the range, right? And so we still need to support a point update. But now when we walk down the tree, like you don't know what to change this to yet, right?
Yep.
Because we don't know what the old value was. We have to reach maybe the leaf node to find the old value, and we're changing it. And so we don't know what the sum is going to change by yet. We need to walk back down first, edit it, and then the above node can understand what is the new sum.
I see.
I don't know if that makes sense.
Yeah.
In this case, you might be right. I think that just with a simple max operation, you can edit it as you walk down. But just as a general, how segment trees are usually implemented and what's the most logical, repeatable approach, we'll look in the code, but it's going to kind of work like this. But sure, you could do it the way you've listed.
Yeah, that makes sense for the range queries.
Yeah. Or I think a more complex thing is if you update the node to a smaller value, like a 1, you can't actually like edit this value as we're dropping down, because maybe this node says the max was 5 and we actually had 2 5s in a range and we only edited one of them to maybe a 1. The max is still 5. But if the array just had 1 5 in it and we edited it to a 1, the max changes. So like you can't actually know.
I see.
Yeah.
I see.
It'll make more sense when we get to the code, but
Yeah,
that's the rough
that
idea.
makes 100% sense. Yeah.
Right.
Like,
Okay.
but
So
like
that's
when you get to the
Mhm.
leaf, you know it's gonna change for sure because it's that one
Right.
index. But then you have to bubble it up. Like,
Right. Okay. So that's how we do an update in log n. And now we want to ask, what is the maximum in the range? Okay, I'm going to draw a second tree because this is a fair bit harder. I'll just draw a few nodes for now. So we have all of these pieces, like these pre-computed data points, right? So let's say we asked for, I'm on this tree on the right now. What is the max from 0 to 5? So that's our query. That's like really convenient because we already have this pre-computed piece of data that exactly is storing the max from 0 to 5, right?
Mhm.
Let's say that's 5. So that's a good kind of outcome. But in practice, the queries are not going to be so nice, right? Like if the query is, what is the max from 0 to 9? We don't have anything that's pre-computed for that exact query. We have this 0 to 10, but that's not 0 to 9. And it's even more annoying because this 0 to 10, what is the actual max? It's 10. And it's 10 at the 10th index specifically, just based on our input array.
yeah.
So we can't even like kind of take this information and then cancel out the 10th number and figure out that the max is 9 because you can't really invert maxes, right? We can't say, okay, the max isn't 10. I'm going to like subtract it or anything. Like a sum you can invert. If the sum is 10 and we know we need to remove 1 from it, you can invert that, but you can't invert a max. So what we are going to do is we're going to figure out a way to take this query and then decompose it into a bunch of these smaller pieces, these pre-computed pieces, and we're going to decompose it into at most log n of them, right? So if we can take log n pre-computed pieces and we just look at the max of every single one of those pre-computed pieces, obviously we're going to get the max of the whole thing, right?
Yeah.
So like maybe this 0 to 9 query, that's going to decompose into, here's a pre-computed piece from 0 to 5. Maybe 6 to 7 is a pre-computed piece. 8 to 9 is a pre-computed piece. And then now if we just take the max of all of these, we're going to get some answer, right? And my claim is we can always do this in at most log n pre-computed pieces. So here's where it gets a little bit tricky to explain. We're going to start at the root node again, just like our point update, and we're going to say, I'm looking for 0 to 9. Well, 0 to 9 does not cleanly intersect with this 0 to 10 range, right? So we kind of need to look at both children to get some data. We cannot stop here at this 10 and take the data because 0 to 10 is too big. So let's look left. 0 to 5. This cooperates nicely with our 0 to 9 query because 0 to 5 is contained inside 0 to 9.
Yep.
Right? And so we can say, okay, this is going to be one of the pieces that we use. So we're just going to stop here immediately and say, okay, we're going to use that in our answer. Let's look at 6 to 10. 6 to 10, again, does not cooperate nicely with our query. So we need to, again, jump to 2 nodes. So let's say this left region is 6 to 8, and this right region is 9 to 10. Again, we're going to jump left. The 6 to 8 cooperates really nicely, so we're going to take that and say this is going to be part of our query. The 9 to 10 does not cooperate. We need to jump even more. And now this left node is just 9 to 9, and this right node is 10 to 10. When we get to this 9, we're going to use that in our final result. and then this 10 just gets discarded because it's out of range.
Mhm.
So we figured out these 3 pre-computed pieces we need. We're going to take the max of all of them, and that's our answer. And what is the proof that we visit at most log n nodes here? Well, this is where it gets kind of trippy. So if you imagine one layer of this tree, I'm drawing a bit below now.
Mhm.
Like, these are contiguous ranges. So maybe we have 1 to, this is a bad example, 1 to 100, 100. Let's make this 10 to 100, 101 to 200. Sorry, one sec.
Yeah, I think it'll make a lot. It makes a lot of sense, but when I see the code too, it's gonna click even harder.
We will get to that in a sec. We're almost done. Okay, let's say, so remember, inside a layer, like if we scroll back up at this tree, the layers are always contiguous. So if this side is 6 to 8 over here,
Yep.
then like the node on the right is going to be the next range, like 9 to 10, and so on, right?
Yep.
Just flat per level, they're contiguous. Okay, so this represents one layer of our tree, this diagram below. And let's say our query is 1 to 1000.
Mm-hmm.
What's going to happen is we might jump to the left and say, okay, this 10 to 100, or maybe, shoot, this is kind of getting messy here.
Are we allowed to like just jump right to the right of that guy? Like on the same level?
That's not how we're going to do it mechanically. But I think what I'm trying to explain, I'm not going to try to draw it here because it's getting a bit messy, is per level, we are going to visit at most 4 nodes per level. And since there's log n levels, we're going to visit at most 4 log n nodes. And the reason that is because if we visited 4 nodes in a level and we have some query range, the inner 2 nodes are always going to be like fully contained inside our query, and we're going to get to stop immediately. And the outer nodes are the only ones that have a chance to like make us jump to two nodes in the next level. And so that is going to cap us at 4 nodes per level. If that doesn't really make sense, it'll probably make more sense when it gets to the code.
Yeah, it makes sense. Why we could only hit log n.
Right. Okay. So with that in mind, let's implement a segment tree that can do a range. Let me think. We want a range max query, and we want a point update. So let's go to the code. I'm going to open is there already a thing? I don't know how to go there. Okay, yeah. Okay, so this is I'm just going to kind of seed it here before I talk about it. Okay. So let's say, what are the goals? Give an input array. These operations. Does that make sense? These are the operations we want to support.
Yeah, just support one specific index change and then query like some range where LNR is inclusive.
Yeah, LNR is inclusive. At least that's how I do it. So we want to start. Now, in that drawing, we used a tree. And you can use a tree. The issue is trees use pointers, and pointers are slow. We're going to use an array. You've probably seen that before. Like if you've implemented a heap or seen how a heap is implemented, you think of it as a tree, but you actually use an array. And so the trick with that is like, let's say we can imagine the root node as node 1, and then the left child is going to be node 2, and the right child is going to be node 3. So children of node x are 2 times x and 2 times x plus 1. So like the left child of 2 is going to be 4, right? And the right child is going to be 5. So these numbers are going to be indices in an array. So we're going to actually have tree represented as an array, and then tree of 1, that's like the root node, right?
Yep.
Okay, so let's start by...
How do you get the parent again? Like there's a parent formula.
Yeah,
right?
you can just floor divide by 2. So like 6 floor divided by 2 is 3. 7 floor divided by 2 is 3. But in the second tree, we're not ever going to need to kind of do that because we're going to use recursion. It's going to help us with that. So let's do this. First, I'm going to take this input array. That's our actual input data. And we're going to build the tree. I'm going to grab some variables here. We're going to take an n because n is just like a useful thing to have, right? And then we're going to create this tree, which is initially going to have no values in it. And it's going to be sized 4 by n. This is a little bit weird, but essentially we're taking all of these indices for every node, and 4n is kind of a safe bound that if we follow this rule, this children mapping rule, we're never going to exceed like 4 times n. I'm not going to go over that now. It's just a little bit of math with like the log, you double your value each time you go down. 4n, safe upper bound, right? And all of the data, so like tree of node is going to stores data about that node. And what data were we storing?
That's just like the array for 1 to 10? It's
just an array. Yep. This entire tree that we drew is represented by this single array.
Okay.
And so what is the root node? Remember, root is 1, index 1. So index 0 goes unused. You could make the root 0, but by convention, a lot of people make it 1.
Makes sense.
So we are storing the max. We're storing the max inside every node. So tree of 1 is going to store the max for indices 0, ... n minus 1, right? Okay. We're going to need to seed the values of the tree. So I'm going to call a build function. And this will look a bit odd for a sec. But this recursive function is, do I have to do it like this? Is this happy now? Okay, yeah. This build function is going to seed all of the data. So what are the parameters of this? Node I is the node index. So the root is index 1. And again, that's the index in the tree. That's like we're at some node in the tree. TL and TR stand for tree left and tree right. And that corresponds to the bounds that this tree node is responsible for. Like remember in the drawing, root node was responsible for 0 to 10, right? So tree left was 0, tree right was 10. But when we dropped by 1 to the left child, we had this range. So tree left is 0, tree right is 5, right?
Yep.
We could kind of like pre-compute these boundaries and store them somewhere. And then every time I'm at a tree node and I know the node index, I can just look up the indices. But it's more common to always just kind of pass these through the recursive functions. So we know that we start at the root has range 0 to n minus 1. So there's a few things that need to happen because it's recursion. There is a base case. What is the base case? Is if tree left equals tree right, we're at a leaf node, right? We're at that bottom layer. What do we want to do? We just want to fill in the value for that tree, right? And then let me grab this array. So what we're saying here is every node stores the max. The max of a leaf node that corresponds to one index is just the element in that array itself. Does that make sense?
Yep.
Right.
What's
So this
node?
is the base case.
How come we're storing it node? Okay. So on the first index, we're gonna store. Okay. Makes sense.
Right. Okay. But when there's not a base case, we want to recurse. We have two children. We need to build those children first, and then we need to aggregate the data up. It's just like tree recursion.
Yeah.
So we're going to compute something called TM. This is just like the dividing point. So if our node corresponds to this range, we want a left node like this and a right node like this, right?
Yep.
So TM is just gonna, kind of point to like one of these middle things.
Yep.
So we're gonna need to build the left recursively. And what is the left node index, the left child?
The left would probably be TL to mid.
So remember, node index is the position in our
Oh.
tree array.
Okay, wait, let me
And
take a
we have this like rule for how these indices work, right?
Yeah, it's gonna be +1 and the other one's gonna be like, or node I +1. The other one, the right is gonna be node I +2.
What's the left child of 3?
Yeah, it's gonna be 6. So it's gonna be like you're gonna multiply by your level or something.
So yeah, so it's literally just the left child is double and the right child is double +1.
Okay, makes sense.
That's how it's like virtual indexing. Heaps kind of work the same way.
Yeah.
So over here, we're gonna pass in 2 times node I, right? This is like
Yeah, that makes sense.
recursively build the left, right? And then the tree left range stays the same because we're at 0, 10. Tree left is 0, tree right is 10. When we build out the 0 to 5 range, it's the same thing. And we're gonna say TM, which we've computed. We'll say TM is 5. And then we need to recursively build the right.
Yeah, lots of parallels to heaps here. Like once you
Yeah.
learn heaps, this
It's
is gonna
super
go pretty. You'll know a lot of what's going on here.
Yeah. So we recursively build these two. So now we've computed the max inside these two ranges. Now we can compute the max inside our bigger range, inside this like root range, right? How do we do that?
Well, we need to
We
return the
just-
max of these guys, no?
Well, we don't actually even need to return them because they'll be stored in the tree.
I see.
By the time these finish calling, their data will be stored in the tree, so we can just update our tree directly. It's just like recursion. You see what I mean?
Oh, okay. I see. Yeah.
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 That's all it is. Okay.
That
So
makes sense. Because I was thinking
built
these return the max, like left max and right max,
They-
and we
they
just store it.
they don't even return anything. Like this function isn't returning anything. You could do it that way. But we're doing it slightly differently. We just store it in the tree and then we just read from the tree.
I see.
It's the same thing. Okay. So that's the build phase. We need to do a point update now.
And just accessing this node right here, it's not actually accessing a specific index because it's actually accessing a range. Well, when it says tree, because that represents a range. So when we say self.node of this of like 2 or 3 or 6, it's giving us a specific range. Or if it
It's
says 3,
giving us pre-computed data about a specific range, right? Because that's what the segment tree is. Each node has data about a range. It's really trippy to think about, but if you do it a few times, you'll get the hang of it.
That makes sense. I think
Right.
I get it.
Okay, so now we need a function point update. So this is going to overwrite the value at some index with a new value. Right. And typically this is like public interface. Like we're going to keep this really clean. Whoever is calling the segment tree kind of just wants to see this interface. But internally, we're going to have a more complex recursive one, which I will explain in a sec. And the public interface is going to just call this. Okay, so how does the point update work? We start at the root of the tree, and we need to just walk down and find that point, right? So let's go over the parameters again. Node I corresponds to the current position in the tree that we are. TL and TR are the boundaries of that tree node. And then IDX in new value, that was the original query. Which index do we need to find? What is the new value we need to overwrite it with, right? So there's going to be, again, a base case. If we're at a leaf node, that implies we found the index we were looking for. How do we overwrite it? How do we overwrite the pre-computed data there? We literally just replace it, right? We're saying update that data with the new value. Because remember, this data is a leaf node. It corresponds to one index.
Yep.
And it's guaranteed that we're at like the exact index we were looking for. Okay. Otherwise, let's say we're in 0 to 10, trying to find index 7 leaf node, right? So we're going to compute the middle, which let's say this is 5, like the middle of 10. Which way do we need to jump? Because we need to jump one way.
Yeah, it's like there's gonna be a conditional here. If node I is greater than TM.
Not close, not node I. Node I is just the index in the tree data.
Oh, sorry, if index there.
Yeah, if index. So if the index is less than TM, we need to jump left, right? So we're going to recurse. How do we update this node index? It's just double it when we jump left. And these are the boundaries. The left edge stays the same, right? If we jump from 0.10 to like 0.5, this left edge, 0 stays the same, but the right edge gets replaced with TM. Otherwise, we're going to jump right. All right, do you want to try this one?
If the index is less than T or equal TM, then yeah. If so self. So we're gonna go point update.
Mm-hmm.
And we need to jump right. So we're gonna go 2 times node I plus 1.
Yeah.
Because that's gonna get the right child.
Mm-hmm.
What's TL? The left side. That's gonna be like TM plus 1.
Exactly, yeah.
And then TR index. What's index again?
Index is the original index that we're trying to overwrite.
Oh, okay. Yeah. Okay.
Yeah, no, this is great. So index and new value, we just like keep passing it through, right? Those don't ever change. Okay, so now at this point, if you remember how recursion works, we've like jumped all the way down and we found the leaf node. Now we're bubbling up data. We've recomputed the max at one of our children. And so now we need to recompute the max at like this tree node, right? So tree of this node index, it's going to be the max of the 2 children, because one of those children might have changed, right? We walked down some path, updated a value, we're bubbling back up, we're recomputing things as we go back up.
Yeah, and like we know our children are within our range. Like our children capture our range.
Our children exactly capture our range. It's just split into 2. And so it's safe to just do it like this. Right. Recompute. And that's all it is. That updates a point. That takes login time. Now, finally, we're going to need a query max. And again, I'm going to make this like kind of public interface, which is convenient. And then I'm going to make a worse recursive interface.
What do you mean by worse?
Not worse, but like in this recursive function, we have all of this like random variables.
I see.
But when I'm calling the segment tree, I don't want to like think about these. I just
see.
want to say update the value at this index. So I
Makes
make a
sense.
wrapper function.
Yeah.
So same thing here.
Makes sense.
From what is this? Node index, tree left, tree right. Okay. Yeah. So let's go over the parameters of this private interface. Node index, again, that's just corresponds to where we are in the tree, the data. Tree left, tree right, that's the range. QL and QR is query left and query right. So there's two separate left and rights here. We're asking what is the max from QL to QR. That is separate from what are the bounds of the current tree node we're at, right? I care about the max in this range. This was that last confusing drawing we did where I showed there's like 4 log n nodes per query, and we kind of have to decompose the query into pieces. So there's a few cases here.
I see.
Let's say that, what's the cleanest way to implement this? Let's say that our tree node corresponds to like 0 to 5.
So TLTR here is just telling you the range of that. So node is going to tell you like you're on node 1.
Right.
TLTR is going to tell you the range.
It just tells you the range that this node
captures. Okay.
You could literally compute those and just store them somewhere in an array and like look it up, but it's just easier to pass it through the recursive
Makes
calls.
sense. Makes sense.
Yeah. Okay. So let's say we want like the max in this range from 8 to 10, and maybe our tree node only corresponds to 0 to 5. So this is a completely out of bounds case, right?
Would it even get to that case?
It depending how you implement it, the way it works is like you can take your tree node and you can always just recursively query both children, and one of them might be out of bounds because it's not relevant.
Yeah. Like you don't want to, you can handle that edge case in the parent, but just let it recurse and just exit.
I actually typically handle the case in the parent, so I never let this happen.
Okay.
But you can kind of do it either way. So let's just say completely out of bounds. So when are we out of bounds? It's if the right edge of the query is like smaller than the left edge of the tree, right? So query is 1 to 3, but tree is 4 to 10, right? If this happens, or the other way around, I'm mixing C++ and Python here.
Just 4.
Yeah. If this happens, we're just going to say I'm just going to return this identity value because we care about the max in a range. And if we return negative infinity, that's never going to influence the max. So this is like out of bounds case. Okay. What about
is this Python?
Yeah. Well, that works.
Oh, okay.
This is the same. Yeah,
let
that
me
also
reverse
it. Base case, a leaf node, that's another potential case. So if tree left equals tree right, what is the max? Well, it's literally just that tree's value, right?
Yeah.
Okay. Otherwise, we recurse. Left max. It's the same thing, right? We figure out what is the left max of our child, what is the right max.
The segment tree might be a little simpler than the binary index tree.
Yeah, I don't like that data structure.
But you could just do the same exact stuff with this. Seems like you
segment tree can do a lot more.
But like it encapsulates that one though. You can like there's no need to even learn binary index tree that it.
Yeah, a segment tree can do everything that a Fenwick tree can do.
I see.
The Fenwick tree has a smaller constant factor.
I see.
But in practice, it doesn't really matter that much. So we've gotten the max from our left and right. And now we're just going to return the max of those two. So this is our entire segment tree. Let's test it with this LeetCode problem.
Wait, let's see. QR, if it's less.
That's if the query range doesn't even intersect with our tree nodes.
What if it does, but it's like within?
Right. So this is kind of that argument where there's this is actually like the partial intersection case. But it's a little bit confusing because it feels like you are saying, you know, what if our tree is like 0 to 10, but the query is 0 to 8? Obviously, we don't want to just return the max of this entire node, right?
Yeah.
Oh wait, I think I'm missing a case. Good catch. We have a fourth case. Oops. So this is the fully contained case. This is if our tree node is fully contained in the query. So like tree equals 3 to 4, right? We can stop here. This is when we select that piece that's going to contribute to our result. So if this case, if we're fully contained, we can immediately return this value. And then the partial intersection is a recursive process. Yeah, segment tree is kind of hard to wrap your head around. It has taken me a lot of time and implementing it a lot and thinking about it a lot to get very comfortable. So if you are not following 100% or you have some doubts about things, that's super normal.
Yeah.
But just directionally, just understanding how it works.
Yeah.
This concept.
So this fully contained. Yeah. So when we get a certain part of the tree and it's just in there, like we have a range between 3 and 4, just straight up just return that value because that's
right. Because we're decomposing the query into log n pieces, and so that's one of the pieces. We're saying take this piece. It's going to contribute to the answer. We get a bunch of these small pieces, and we take the max of all of those.
Yeah. I need to sit down and just think about the case when it's the partial intersection.
Yeah, the partial intersection is really trippy. I didn't explain it very well. Give me 1 sec.
I think if I look at it hard enough, it'll make sense.
I'm just checking one thing. Okay. So now we're going to solve LeetCode problem 300. Do you want to send an invite link for that?
Yep.
This is all tying back the relevance to yesterday's hard, which was super, super hard.
Yeah. No, I'd rather not do that super hard one because I haven't really even done segment.
No, yeah, we're not actually going to implement it or anything. I just want to show you the thought process behind it. So
I like this strategy for sure.
Yeah. It's also like a bunch of people watching this are probably trying to learn for interviews. And that last question is just not going to be relevant for interviews. It's too complicated.
Yeah, I had to just dip out my last. You have to leave it too. Try to, like that last link I sent you.
Wait, what are you asking?
Okay, never mind. I got you a new link. Because it only allows you one link at a time.
Oh, I see. Okay. Yeah. So we can both type in this, right?
Yep. I could see it's like interactive code editor. It's pretty sick.
Okay. So you can see an empty entry, right?
Yep.
Okay. So let's take that segment tree template, and I hope I coded it right, and paste it in.
Oh, me?
Yeah.
Okay.
I'm gonna have you kind of code it.
Okay, we're gonna put it. We're going longest increasing subsequence.
Yep. And this is
probably throw it at the bottom. Huh?
Sure. Yeah. This is an optimized version of this. If you look at the constraints, it's 2500 and is less than or equal to 2500. So n squared is a permissible solution, but we're gonna kind of learn to do n log n.
How the heck did I solve
Right.
this?
Yeah, and it even says follow up. Can you come up with an n log n version? So one of the ways to do that is a similar approach to yesterday's question. So
I did some DP
in this,
for initially.
yeah, the n squared for this is a normal DP, and then the n log n is like combining a segment tree with DP, which is an interesting idea. You could pass an array to the segment tree, but that array itself is a dynamic programming array. We'll see when we write it. So in this problem, it's tricky because we basically have two dimensions. We need to find the longest increasing subsequence. So that means that the indices, right? If our subsequence is like this, it's some, what's a good notation? It's like some set of indices, right? That we select, not necessarily the actual 0th, 1st, and 2nd. We'll call the array. Then we're gonna pick like some set of indices, and the indices have to be in increasing order, right? Because we need to pick a subsequence, like it's a subsequence, so the indices are in increasing order, but then the actual values.
Subsequence like delete stuff in that. You can delete anything in the middle as well between characters.
The actual values also need to increase. So there's basically two dimensions that we kind of need to manage here, and that's why it's tricky. What we can do is we can fix one of the dimensions. If we process these elements in some way from left to right, we are enforcing this first constraint, right? We're enforcing that we're pulling in the indices in order, and we don't need to worry about that. But we do need to worry about this index order, or sorry, this value order. So process elements in index order. That's just processing them left to right, which is quite simple. So it's going to be like for loop on the elements left to right. Now, when we look at this, what's a good example? Let's look at this example 2, where we have this array. And let's say we already have like picked this first 0 as the start of some increasing subsequence. And now I'm going to look at this 1, right? This 1 can be appended to the end of some subsequence, right? Which types of subsequences can it be appended to?
Is there anything less than 1?
Anything that ends less than 1, right?
Yeah.
Okay, so that's like, what does that sound like? That sounds like a range query, right? Because we care about something like this. And which of those subsequences specifically do we care about? We care about the one with the biggest length, right? Like if we had a subsequence like this, -1, 0, that's length 2. And then we had a subsequence like this is only length 1.
Yeah.
Appending a 1. Obviously, we're going to append the 1 to the longer one.
Yeah, for sure.
Provided that it fits this condition. So I want to do range query. What is the longest subsequence that has an ending less than 1, right? Once I find that, current longest is length 2. Then what do I want to do? I want to do a point update. Set a new subsequence of length 3 that ends in 1, right? That's all it is. These are the interfaces for our segment tree. So we're going to loop through the array. Let's actually just walk through this this first example, like what would happen in the segment tree. We're going to look at this 10. And right now our segment tree, let's just say it has like empty data. We haven't put anything. What is the longest subsequence that has an ending less than 10, there's none, right? So we don't do anything with that. But now we can say, okay, we can form a brand new subsequence of length 1 that ends in 10, right? Now we're going to process this next element, the 9. What is the longest subsequence that ends in a number less than 9? There isn't any. So we can't append the 9 to the end of anything, but we can do a point update. We can say the subsequence with length 1 is now like 9. That's obviously better than 10, right?
Because it's
Same thing.
smaller. Like
Yeah, we get to this 2. We're going to overwrite it. Okay, now we get to this 5. What is the length of the longest subsequence that ends in a number less than 5? Well, the length is 1. We know that because that is what our like tree node is storing. Longest subsequence, right? And so then we can update. We can create a new sequence of length 2. We can do a point update, create a sequence of length 2 ending in 5. And each of these operations takes log n time, and we're going to do n of them. So that is, I don't know if we should necessarily implement it because it also, there's like negatives in this problem, and so you have to shift everything into the positive range, and I think it might get a bit messy. So I'll leave that as an exercise for you to try to implement.
Nice.
But a very quick, just 2-minute explanation of that hard problem from yesterday is we are trying to find an increasing subsequence. The indices have to be increasing, the values have to be increasing, and then there's a third parameter relating to the deletions, and that has to be like not decreasing. So you basically have 3 constraints. You don't have to really understand what those constraints are, but it's like a third constraint. And so you would use something like a 2-dimensional segment tree. So every node in the segment tree, instead of storing a max, it stores an entire second segment tree. And that's just adding a dimension. So that makes like queries become log squared n.
Damn.
Yeah, no, it's crazy. And then so the overall solution is n log squared n with 2D segment tree. But practically speaking, that was too slow. So you can use the bit, like what you said, / Fenwick tree, same thing. 2D version, faster, constant speed. It's the same complexity. I got that to pass in around 1 second in C++.
Wow.
But then I think the intended solution is clever observation about the constraints. There's like 3 dimensions in that. But you could actually drop one of the dimensions in a way. And because you drop a dimension, it ends up just being an n log n style list, like this problem. So that's how to solve that.
Wait, for this question, what are the nodes? What are the ranges that it's gonna be in the tree, in our?
Yeah. So the tree is going to store the max of some subsequence ending in a value range. So like in the drawing examples, we looked at indices. So root node corresponds to indices, say 0 to 10.
Yeah.
But in this one, the root node is going to correspond to subsequences where the last element ends in a number in this value range. Does that make sense? So
okay, so it's capturing all of the subsequences that end in anything from 0 to 10.
Yeah, and so
then,
the
like,
left half would be 0 to 5.
Okay, so we can easily find like the number. So pretty much the leaf node, say 2. This is number of or longest sequence that ends in 2.
Subsequence ending in 2 exactly.
Okay.
And right, and so because we need to do queries, like if we look at this process we were doing earlier, when I'm looking at this 5 and I want to put this 5 somewhere, I want the longest subsequence that ends in a number less than 5, right?
Yeah.
So that's like saying query longest subsequence. Let's say like the minimum is 0. That's allowed. That ends in a number in this value range. It would be from like 0 to 4, right?
Wait, sorry. Someone's saying something in the chat. Longest subsequence that ends in a number in this value range. Okay.
Because we're trying to insert a 5.
But like what I'm trying to figure out is we're trying to insert a 5 that's a value.
Yeah. And where can we insert a 5? Against any subsequence that ends in a 0, 1, 2, 3, or 4.
Okay. So we're gonna be like, okay. Oh, so it's gonna be like, okay, pretend like it's 5. And then we know for all these values less than 5, like 0 to 4, this is the longest sequence. So I can increase that and then store it as like, that makes sense. And I'll store it as 5. Yeah, that makes a lot of sense.
That's a point update, yeah.
Yeah. Okay.
So, maybe I didn't teach this in the best way because there's two concepts. There's segment trees built on indices, and there's segment trees built on values. So this one is built on values.
Yeah. That's like with a lot of things. It's like you can go by indices or values, even like with binary search.
So like the array we would seed the segment tree with is like, it's a bunch of zeros at first, right? Because we don't have any subsequences built. But the length of this array is like the size of the universe, where universe means like all values that exist in the problem. So in this case, it's up to 1e4 is the biggest number, right? So we might have 0, 0, 0, like 1e4 times. What is the longest subsequence that ends in 0? What's the longest subsequence that ends in 1? Ends in 2, all the way up to 10,000.
Yeah, that makes sense.
Yeah.
Wait, 1 to the e to the 4.
There's gonna be that many zeros in the initial array.
Wouldn't the initial array depend on the largest value in nums?
No, because for starters, let's look at this constraint where like the value range of nums can be negative. Let's just assume it can't be negative to simplify things. Okay, so nums of I can be up to 10,000, right? Yeah. That's a maximum value. So what do we care about? We care about longest subsequence ending in a 0, longest subsequence ending in a 1, longest subsequence ending in a 2. How many times do we need to write that out?
Okay, wait. Nums I can be up to 10,000. 10,000 times, I guess, because we just
the biggest case we care about is like the longest subsequence ending in 10,000, because that's the maximum the array element can be.
Yeah.
So this is the range that our segment tree needs to operate over.
Yeah. That makes sense.
So the initial array we give, because initially we haven't built any subsequences, so everything is going to be a 0. Like the longest subsequence ending in 0, that's this first one, that's 0. We haven't built any subsequences. What about ending in 1, ending in 2, so on, and that's going to be size 10,000 array.
Yep.
That's the actual array we pass to the segment tree.
Yep. Okay,
yeah.
Cool. All right. Awesome. That's actually a really good crash course. I think I need to... You have any homework for me? Like questions with value, which is this one, but what about one that's just straight on indices?
Yeah, I think the most famous one is called range sum query mutable. That is problem 307. If you read it, you'll pretty directly see.
So 307 and 300.
Yeah, 300 is like a fair bit harder, but if you can do 307, that's great. Or
Cool.
Yeah.
Nice. No, honestly, that was super helpful. We gotta run more of these.
Yeah.
Chat, any questions from y'all?
I'm also going to be practicing segment trees after this.
Yeah.
Yeah.
Yeah, I'm gonna do so. I'll run the homework and then I'll let you know if I have questions.
Yeah.
Cool. I guess yeah. No one's really saying anything.
Mm.
So what are you up to now? You're gonna go grind some more.
Yeah, I want to practice more segment tree problems because this is the basic segment tree we've gone over, but there's way more complicated stuff you can do. You can do multi-dimensional segment trees. You can do, instead of a point update, you can do a range update, like I said, with a lazy segment tree. You can do something called persistent segment trees.
Interesting.
You can have merge sort trees where every node stores like a list of data. And so I want to practice some of the more tricky applications
Yep.
of segment trees. That's what I'm going to be working on.
Nice.
Like some of the CSES problems I'm doing.
All right, man. Have fun. Thanks for showing me how to do this.
Yeah. Let me know how it goes.
I'm gonna compete again next week, and like if I get stumped, hopefully you can go on another session and
Yeah.
teach me that. I hope you found it useful as well on your side, like teaching it through.
Oh, yeah, for sure. That's always helpful.
All right.
Okay. Have a good one.
See you, man. Peace. Chat, how was that for y'all? Instructive or what? W's. Why would it be pre-recorded? Becca, what's up, man? How you doing? Yeah. You want me to go over Q3? Kinjal? Okay, I got you. Let me just change. All right, I'll explain it. Give me a sec. Then I'm gonna practice segment trees right after. Yeah, I'll go through this. I solved this one. It took me a little bit of time, but I was able to figure out. But it required a lot of thinking. Yeah, I'll walk through the solution for this. This is a pretty good question. Let me bring up. Let me try to explain. Oh, okay. No, we're gonna get to it. We'll get to it. I'll teach you, and it will make sense. You have honestly with this question, I recorded me actually going through the question. Let me see if I can bring it up, and you could see me actually grinding it through. I'll post this video separately so you could see how I think through problems. Oh, dude, I don't think I recorded it. Okay, let's just like cancel all this code and discuss how we're gonna think about it. Give me like 30 seconds. Let me stretch, stand up real quick, because that was a whole 1 hour session going deep on segment trees. Hold up, wait a minute. I'll be right back. Give me like 30 seconds. How's everyone's day going so far though? Was the last like session instructive or what? I'm gonna chug some creatine real quick. Nardo, I'll answer that in a sec. Just drinking my creatine. Nardo, what's your level? Nardo, we should run a mock interview. I want to see where you're at with your leak coding skills. You got my numbers, so message me and we'll set up a mock, or like message me on like send me your LinkedIn or something. Man, do the Pro to 75, bro. Let's go. All right. Yo, the thing too with my website is like I don't have as much time to spend on it. That's what I'm saying. Like if I had unlimited time to spend on that website, bro, I'll be helping people out way easier. I'll be able to give way better reviews. I'll be able to give way better guides, stuff like that. Like right now, I barely have any time to do it, which is annoying. That's why I feel like I might have to quit my job. Or I'm gonna take some PTO or some sick days to just for sure. Nah, I'm gonna fix that up tonight. But I got some good ideas from the chat, low key. Bro, the thing is like I don't I feel like how much yeah. I feel like I can make dude I'm just trying to figure out how much I really need in order to survive. But the thing is I'm just making a good amount of money at Meta. So I'm all the time I'm calculating, I'm like, yo man, what is it gonna take for me to quit? What is it gonna take? I feel like just doing I don't even know. I need to come up with a plan. Kinjal, are you here still? Let's go through this. I'm about to go to Europe and stuff, dropping a bag on that, so I need to go make it back. Kinjal, ready? Let me know when you're ready and we'll run it. Alright, perfect. So a lot of people So what were you saying? What was hard for you about this question? Or like what made it difficult? Okay. Yeah, so LeetCode 3919, minimum cost to move between indices. So in chat, they're saying in general, it was just hard to understand the problem and actually think about it. And I did this contest. I have a video of me actually like thinking through this process. But I'll explain the question and then we'll talk about the intuition and then try to reason about how to get to an optimal solution here. Or at least like some solution. So you are given an integer array nums where nums is strictly increasing. So this is an important part of the question that you need to take into account. This parameter nums is strictly increasing. Right? So for each index x, let closest x be the adjacent index such that the absolute number of x minus nums of y is minimized. So there's also what this is saying is like for each index, the closest we're gonna calculate the closest index by taking which is the closest value from adjacent indices. So for example, let's just go for this case. If what's the closest to index 1? Well, we have to look at index 0 and index 2. So to my left, the distance is 3. to my right, the distance is 5. So the closest is actually index 0. So the left is index 0. Right is index 1. Right? And you're only allowed to look at the adjacent index, the one to the left and the one to the right. If they're both the same, you just take the smaller index. So if they're both 3, for example, then you just take left. So this is what it's saying. For each index, calculate the closest. And then what it's going to say, from any index x, you can move in 2 ways. To an index y. So what it's telling you is we're basically going to be traveling through. We're going to be traveling through an array. And that's what these queries are telling you. It's telling you we're going to travel from Li to Ri. So that's what they're going to give you, queries. We are travel from Li to Ri. And the way that it's going to tell you the only way that we can travel. We can travel from any index. We can either travel, or, and it gives you the way we're traveling. The way we travel through an array is either choose any index and move to that point, but take the difference of index and that point. Or just choose the closest with a cost of 1. Right? So, like, one thing that you can think about here, does the question make sense so far? Or, so that's what's saying here. We're given a bunch of queries and we need to calculate the minimum total cost to move from minimum. Like, this is what we actually want to solve. Right? So let's just walk through with a lot of these. It's hard to solve it just sitting there thinking about it. You have to sort of work through the cases to understand what the question is asking a lot of the times as well. Right? So let's look at this first case. -5, -2, -3. So we're given -5, -2, -3. The first thing we're going to want to do is create a closest array. I mean, let's just work through the bigger example, honestly. So let's just make sure we understand how closest works. So the closest from index 0 is going to be 1. Because it only has one neighbor to the right. And actually the same thing with, so this is index 0, 1, 2, 3. The same thing with this index. So that. The same thing with the last index. It's just going to be the length of the array minus like 1. Yeah. So 2. What's the closest index to 2? It's 3. So it's actually going to be, or what's the closest value from its neighbors? It's going to be 3. So it's going to be index 2 here. What about 3? The closest index to 3, or value 3, the distance is 1. Through here, the distance is 6. So 1 is less than 6, so we're going to grab index 1. So this is how the closest array works, right? So the key intuition here, like we have to use all of the knowledge that we know about the question. We know that nums is strictly increasing. That means every value is greater than, so it's at minimum going to be like 1. Or every value is greater than or equal to, so it has to be at least something like this. It's never gonna be like another 5. Or anything less than 5. So we're gonna be asked, what if we want to travel from 2 to 9? Right? Like, since it's strictly increasing, we know that if we can look at the closest, if we want to follow the closest, if the closest is greater than our index, we're always gonna want to take that closest. That's greedy. Right. We're always gonna want to take that closest because we know that like the way we travel through an array is we choose any index, or we choose the closest with a cost of 1. Like, we know the cost. We know that if the closest moves us ahead, we should always take that because it's gonna be minimal. Because also that this is strictly increasing, there's no chance that we can move ahead with 0. Since it's always gonna be larger than another. Like, if the closest leads us above, if the closest like leads us, if the one to our right is closest to us, we're gonna want to take that path because it's always gonna cost 1, and that's gonna be minimal. But then for this one, so suppose we want to get from 2 to 9, right? We want to get, this is left. Yo, Cyclops, what's up? Suppose we want to get from 2 to 9. We know that if we take sit for 2, the closest one is actually, the closest index is actually 3. So we know we should take that one. And that's going to cost us 1. Result equals 1. And then how are we going to get to 9? Well, the closest to 3 is actually 2. So we just can't take closest. And if we want to get to 9, we just have to just straight up jump to 9. Because if we, like, the only way to get to, we never want to move backwards. Because we want to progress towards, if we're trying to get to the right, we're not going to minimize the path by jumping backwards then forwards. Because also we know that the array is strictly increasing. So think about that. Like, there's no point in, if you're here, then you jump backwards and then jump forward again because this is going to cost you more. So you always want to make progress. But for some of them, you can make progress. Suppose you're trying to get from L to R. If there's a couple points in here, and this one's like further, you can actually get to this. You're gonna basically, it's kind of greedy where you want to take as much ones as you can. You want to jump to the, you want to take like the closest one as much time whenever you can. Take the closest. Otherwise, you just have to take whatever. Otherwise, you have to take the other case. Does that make sense? And essentially, to solve it, we're gonna just calculate a prefix sum. We're gonna calculate 2 prefix sums. prefix sum going forward and going backwards. Cyclops, good job, man. I love how you got that job at Airbnb. Congrats. You're about to make a bag. So we're gonna compute a prefix sum forward and backwards. That's kind of the intuition there. So I'll show you what that looks like here. Does that make sense so far, Kinjal? So we're gonna compute a forward prefix sum. And what that's gonna allow us to do is, well, because we need two prefix sums because the prefix we need to be, the queries can go from left to right or right to left. So I'll show you why it works. The prefix sum works going from left to right, or why you need to compute both. So we're gonna compute one for forward and backwards. It's because the closest is gonna change depending on, like, so this is closest. We'll go 1 2 1 2 1 2. Does my intuition so far make sense on this? So what we're gonna do here is we're gonna compute a forward and backwards. So like I said, with forward, we're just gonna want to compute what it's gonna take. So what the prefix sum is gonna tell us is we're to build the prefix sum, we're just gonna kind of, this is the initial array. We're just gonna compute what it's gonna take to go from the start here to the end here. And each point in the prefix sum will tell us what it takes to get to that specific point starting from the start. And then we can do range queries as well after. So if we want to get from 2 to 9, we'll just be able to access that specific part in the prefix sum and then minus it by where it's ending. Because if we know what's the how long did it take to get here from the end or from the start, we subtract that out. And then how long did it take to get to here? So we'll get these two ranges and then we'll subtract out this, and this will tell us how much, or the cost to get from this pointer to the right pointer. So let's start from left to right going forward. So if we have 0 and then the closest one to 0, we should probably we should just jump to 1. 1 is always going to be cheaper. It's always going to be cheaper to take the closest than to take the absolute value between the two. Well, it's always going to be cheaper or equal to, because of the strictly increasing constraint on the problem. So since closest is there, we're just going to take closest. Now, what's the closest from 2 for this one? We could either jump to 3 by taking the absolute value if it's 1, or we could just jump to it using the closest. So that's the case where it's just equal. So now to get from 2 to 3 from the start, it's going to cost us 2, because we could have just took the closest both times. Now if we try to go from 3 to 9, we can't take the closest because the closest is actually 2. So we're just going to have to take the difference here. So that's going to lead us to 8. Isn't the distance between 0 and 2 distance of 2? No, like well, we had to calculate this closest thing. So there's two ways to move. We can either move taking the distance, or we can move taking the closest, and the closest is just the smallest adjacent value, or the closest adjacent index in terms of value, like the adjacent index that's closest in value. So when we say the closest index to 0 is 1, because I mean, it only has one neighbor, but the closest index based on value to 2, or index 1 here, is actually index 2, because there's a distance of only 1 here, but then there's a distance of 2 here. So we're going to just pre-calculate that, and that just sticks. And then that's how we calculate the forward pass. And now you can see, like, we can run any range queries. Suppose that we wanted to go from left to, we wanted to see what's the current. Yeah, I got you. Suppose we wanted to go from 2, like this was the, we ran a query, and it's like we wanted to go from 2 to 9. Then we just we can calculate that easy without. The problem with running a bunch of these queries is we can easily walk it, but we want to be able to calculate an O of 1. That's why we calculate the prefix sum. But essentially, we just access, okay, to get to 9 from the start, it's going to cost us 8. And then to get to this index from the start, it's going to cost us 1. Right? And that will equal 7, essentially. So when we subtract those, if it costs us 8 to get from 0 to 8, or from 0 to 9 here, and it costs us 1 to get from 0 to 2, to get us from 2 to 9 here is going to cost us 7. Right? So now that will answer any queries. That's going to answer any queries where left is less than right. Like when we're traveling left to right. The forward answers any queries where we're traveling from left to right. On forward, queries left to right. And then, like, lastly, there are some queries here where you're gonna want to go backwards, like from 2 to 0. So when you look through this case, like you'll notice right away that if you're going backwards from 2 to 0 instead, like this was the start and this was the finish. Start, finish. The basically the value could be different. It's not the same as, you can't just be like, oh, I'm just gonna go from left to right. It's gonna cost the same because of this closest array. So the closest array, actually, no, if I was to do the reverse, if this was the start of the finish, I can get to here in 1 because that's the closest, and I can get to here in 1. So that's different. So what the prefix sum here is going to be, it's going to cost 0. But to get from 3 to 9, from 9 to 3, it's going to cost 1. Then it's going to cost 1. And then it's going to cost 3. So it's going to be 1 to get to 3. Here it's going to cost another 1 because this is the closest. And then here the closest is actually back to 2, but so that's why to get to this element. So whenever the backwards will allow us to query from right to left. So suppose I wanted to capture from going from this start to this finish. What I'm going to do is it's going to cost me, sorry, this is not 2. This is going to cost me 2, and this is going to cost me 4. So now if I want to get from this start to this finish, I just have to access this index, which is 2, and then also with 0. And then that will give me a distance of 2. So that's why you need to compute the front and backwards And that leads to like my solution. Hopefully that made sense. That's how I thought about that problem. Oh, I can walk through the code. I did this during a contest, so it might not be as clean. Does that make sense? Yeah. But you need to take into account, I don't think this same solution will work if the array wasn't strictly increasing. I don't know. I'll have to think about that. I don't even know if the question makes sense if it's not increasing, if it's even possible. I mean, obviously, everything's possible, but it's gonna be might just be some brute force. Yeah. So this is kind of my code here. So what I'm doing is I'm calculating the closest array. So I know for every index what's the closest. Calculate closest. That's just straight up O of n. And from there, I'm literally, for the 0th index, the closest is always the one to the right. And for the very last element, the closest is always the one to the left of it, because it only has one neighbor. But then for every other index, you have to look at the left neighbor and the right neighbor. You'll take the absolute value distance between the actual value. That'll give you the distance. And the closest index is the one whose value is less than the other one. And I do left is equal to right, because if they're equal, I want to take the left. So this case is left is closest index. Right is closest index. Then I do my forward pass. Do my forward pass here. And this is what I was mentioning before, where we just go from left to right. And if we can take the closest index, if the closest index is greater than my index, I'm gonna take it, because that allows me to move up by 1. This is a greedy, take the greedy choice. Otherwise, I have no other choice but to just take the difference. And since it's strictly increasing as well, right? I don't need to care about jumping to, suppose I'm here and then there's other points in between. I don't need to consider if I need to jump to all the other ones. I just need to consider jumping to this one, because when I jump from this one to this one after, it's already going to capture the distance I traveled earlier. So my goal is to like get to some point in the strictly increasing graph. I just need to look at the next node and try to minimize there. It's a bit greedy. But that's what I'm going to take. The cost is I couldn't just take the next value. Like I couldn't just move up using the closest, so I have to take the absolute value and jump to it, and I go forward. This is how that's how I calculate the forward, and I just do the same thing going backwards. Same code. Dude, even on the contest, I try to write good variable names and stuff in the reverse. And then basically these are when we just calculate. Now we already have the prefix sums. Now we already have the prefix sums. Now we have the queries. If I is less than j, that means we're going from left to right. We can use the forward prefix sum. Otherwise, we'll just use the backward sum, prefix sum, and append it to the result. So we just do that for all the queries, and yeah, it worked. Honestly, I didn't look at like what everyone else was doing, but I think they all kind of did the same thing. Hopefully that makes sense, chat. Hopefully I explained that well and the intuition. How's the audio, by the way? Was my audio good? I think my audio might have been a little bit low, but let me check my recording. The closest 8 is I have no other choice but to just take the difference. And since it's strictly increasing as well. All right, chat, how was that explanation? Did that explanation make sense to you? Do you understand? Yeah, there's a few concepts you have to understand. Honestly, especially in the heat of the moment in the contest, it's very who solved this? Who could have solved this in interview? Like on the spot. Any other? Is there any other questions that y'all like struggled with that I can teach? I'll try to teach it. I'll do one more question, then I'll. Give me a DP problem. Honestly, I haven't done DP in a while, but I'll try to like think about it and decompose it and I know I can get to it. Yeah, the fourth one was hard. Throw me some. Throw me some questions. Got you, man. Got you. Yeah, practice those segment tree questions. Oh my. No way. Yeah, this is some hard DP questions. Yeah, though if Ashan says those are hard, I'm down. Though they might be too hard for me, but I'll try it. Okay. Let me try to embody this hard right on the spot. So we scramble a string S to get a string T using the following algorithm. If the length of string is 1, stop. If the length of the string is greater than 1, do the following. Split the string into 2 non-empty strings at a random index. If the string is S, divide it to X and Y, where S equals X plus Y. Randomly decide to swap the two substrings or to keep them in the same order. After this step, S may become X plus Y or X plus Y. Apply step 1 recursively on each of the two substrings S and Y. Given two strings S and 1 of the same length, return true if S2 is scrambled string of S1, otherwise return false. Now I'm going to hit the gym today right after. Just messaging my friend right now. Try to do some shoulders. Yeah, Ramen, I did the same thing. Given two strings S1 and of the same length. Okay. Two strings. Return true if S2 is a scrambled string of S1. So let's look at this. Let me read this again. How to scramble. If the length, so this is the base case. If length is 1, stop. Otherwise, split the string into two non-empty substrings at a random index. Okay, so if we have like great split into two. We can just pick a random index, and that could just be like GR plus EAT. Randomly decide to swap the two substrings or keep them in the same order. So we can either swap them like this. ET GR. Or just keep it the same. Okay. So what I'm thinking is, since we're splitting, honestly, like, since we're doing split the two. Yeah, it's a random index. So we could also like get G, RET, then GRET. And then from there, I mean, we can split this as well. So what's the most that we could scramble it? Yeah, Ishan, it's basically DP because you're pre-calculating stuff, right? Like it's doing pre-calculation. Or you're pre-computing. Prefix sum is basically is like a form of dynamic programming, I guess I would say. It's in the same category. So one thing that's coming to my mind right now is like if we were to choose the very left index every time, we could reverse the string. So I think there's like one thought that's just going into my mind is I mean, obviously not every. First off, there's conditions for it to be a scrambled version. The first condition is it has to have all the same characters at the same frequencies. The second is, I mean, just because they have all the same characters at the same frequencies, it doesn't necessarily mean that you can build, you could scramble it to get to that version. Not like first condition. Yeah, for sure I'll have more. Ishan's gonna be. What do you want to see from Ishan? You want me to interview him again? You want him to talk to? He has his own channel as well. He's been dropping videos. But if you're talking about like any collabs, like what kind of collabs do you want to see with me and Ishan? That's helpful for y'all. Second, just no, I don't watch soccer. I just watch basketball pretty much. Just because it has. Yeah, I'll put him through a Fang style interview. Like actual digging in. Who you got in the playoffs? I gotta say OKC maybe. I don't know. I'll talk to it, Sean. Y'all drop. Maybe we'll start a thread somewhere of like what videos you want to see, and I'll put him through whatever y'all want to see. As long as he's down, I'm always down. It's good content that needs to be on the internet. Yeah, I was laughing so hard. I was happy about that win. I wanted honestly, I wanted Houston to win. I wanted Houston to win the whole thing. That's my team because I'm a big KD fan. But he, I mean, they got wrecked by the Lakers. So realistically, OKC is gonna win the whole thing. They're pretty dominant. Spurs might have a chance. That would also be crazy. I mean, why not? Why not have the Spurs win? Oh yeah, yeah. Raps, let's go. Honestly, I'm a Cleveland fan though, because I like James Harden. Oh, game sevens are starting now. Probably, probably gotta watch those. But I couldn't really get into the Raps. I'm not from Toronto. I'm not from Toronto, man. I got ops there. Let's see. Second, just because it has all the same cars, freaks, doesn't mean it's a scrambled version. So how do we know if it's a scrambled version? That's the thing. Oh, but the constraints here are crazy, are very small. The length. Honestly, it's like the if we were to just brute force, what's 30 to the power 30? It might be a large number though. me Google that. Well, it's not really. Is that too slow? Can we even hit that? Like, I'm wondering. Yeah, because my solution might be brute force. I mean, an obvious brute force solution would just be just simulate all options, leaf node in recursion or base case in recursion. You check against the scrambled. Yeah, simulate all base case in recursion. You can check against the scrambled. Now I'm just trying to figure out, is there any way that we can actually make this faster? Like I wonder if, because yeah, what we can do is just, but then that's not really dynamic programming or anything. That's just straight up brute force backtracking. But what can we cache on? So there's multiple ways that we can do this. We can split off, split onto this. G plus. I've only done like 70 questions on code forces, and LeetCode I've done 750. So you can do this. Or we can split like this. Nardo, why? What's up? Why am I dim? Let's see. Nardo's a troll, low-key. A, G. So these are the different ones, and then from here, you can scramble them too. So you could also scramble them here. I'm just trying to see if I do the tree, if I write out the tree. What is happening here? I'm trying to figure out. Beef. Beef in the chat. Dude, why does it keep switching to USB? So we split it here. To keep the same order. Again, apply the algorithm. So what I'm thinking is we kind of want to place the R and then we want to see if it's possible to get the rest. So how do we place the R? That's like one way I'm thinking. Like place a R and then try to place the rest. Would that work? Why am I thinking that? No idea. See, let's look at a case when it's false. I feel like it's some sort of out of order. Can we even get to... Why can't we get to A, B, C, D, E? A, B, C, D, E. Can we get C here? Yeah, we can get C here. But there's like some dependencies though. How to get C here? I mean, we could just chop this and put C, D, E right here. Or there's other cases where... Or there's other cases where we put here. Like as long as... Can we get any number to the front? Can we get... This is when you just have to play around with the problem and see what is possible. Okay, if I want to get E to the front, yeah, I just do. What if I want to get D to the front? Well, to get D to the front, I'd split D and then I'd flip it. Yeah, if I want to get anything to the front, I'd have to just take that element and then bring it to the front. But it's going to take all of these. It's going to mess up the dependency because you take all of these to the right and it's going to put it in front of A and B. Are these unique? Oh, it's not unique. Okay, I think we need to be able to track. I think we have a couple intuitions here. First, it needs to have all the same frequencies. Because the thing is, if I take C, D, E, and I want to put C to the front, right? I need to find a C to place in this index. But if I take the C with me, yo, Alpha in the building. We got this scramble string question. So I think what we're gonna want to do is we're gonna want to place that character, but when we place that character, we know we're gonna put a D and E before A and B. So that's gonna mess with A and E, A and B, or this index. Now this index, it used to have. What if now we want to go A? So we'll have to do C, D, E, A, B. Now we're gonna want A there because these are unique. So I'm probably gonna have to take the A and swap the A here. But it's gonna take the B with me. It's gonna take the B for these. Now I'm with D and E, and now there's that mismatch, so it's just false. There's not traditional DP, I don't think. Yeah, back in the days. That's one thing, is that nah, they keep telling me that if I start something, they'll put money in it. That's the main thing why I need to start something. I'm gonna talk to them soon. I'm gonna try to, when I come back from Europe, I need to sit down with them and tell them what I'm thinking, like all my different ideas. So this is what we're expected, right? I don't know. I spent 23 minutes on it. I think I almost solved it though. So we want to get R. So we find a R, and then since there's only one, we're gonna want to put the R here, and then these are gonna go here. G. Because we're gonna want to flip the R. And this is G. Wait, so how's this gonna work? Yeah, This is way hard for an interview, Loki. R. And then we're gonna have to, if we want R there, what are the ways that we can get R to the front? Well, yo, is this just straight brute force though? Because the thing is, I'm trying to optimize it, but I might just be able to brute force it. Yo, tens in the building. If I could just brute force it, I would have solved it like 20 minutes ago, but Man, it's fine. It's good. It's good. It's been fun. Yeah, I'm gonna need a hint on this. How do you get a hint? What do you mean define? I see. Yo, Empower Code, what's up, man? I saw your last comment. Thanks for subbing. Appreciate you. Constraints. Appreciate it. Yeah, we're gonna try to keep this content, keep pumping out this content. It's fun. Try to keep it interesting. Get some good guests on. Yes, sir. Okay, let's look at these hints. We have some state in string S, and we are trying to make it to T. Did you cover any series on DP? Probably at some point. I'll have to look. Honestly, in DP doesn't really come up in interviews as that much. I don't remember when I've ever got asked DP, even at fan companies. Yeah, I'd never seen it. And I've done interviews at pretty much every company at this point. Yeah, maybe wow, they're tweaking. Classic startup, classic startup. What topic should we focus on? I'll give you I have a video on this for sure. This one. And I have a playlist. I need to update it a little bit. Got you. So what are we doing? Start by putting these states into recursive function to see what options you could take from there. So at the start, you want yeah. Okay. Because top down DP always starts with states, and then we think about actions we can take to transition. Okay. Like the only transitions I could see we could take is these might stay the same then, right? TLTR. Or like we're not rearranging anything here because we want to rearrange this. What are these? Are these indices or actual strings? Sean. Okay. Okay. We're gonna say SL. Okay, so for this first pass, well, is it just gonna be like 0, 1, 2, 3, 4, 5, 0, 5? Do we say Ken 0, 5, match 0, 5? We don't know. Or it's no at first. Oh yeah, well, so. Can we know that from now? No, but we kind of need to build up the pieces. Oh, okay, I see, I see. They'll give me the GHA, which I cleared. Then they emailed me about business requirement to change, but result will be valid. Man, just spam them. Keep spamming them. Be like, yo, give me a job. Give me a job. I don't even know what that. I don't really know what he's asking there, but so 0 to 4, 0 to 4. So we're gonna want to branch off. So we're gonna say we have the two cases that we talked about. Oh, I see. Like kind of the base case is if it's at the same index. Oh, okay, I see. Yeah. But what are we gonna save the results on? Okay. Basically, we're gonna try at every midpoint. At every midpoint. But I'm trying to figure out like the reason I didn't think we can do this is what are we caching on? Because every time we shuffle, it's gonna. Oh no, but then we're just gonna know. Like for this index, could it possibly get to this index? And we'll just can 0 to 3 ever equal to 0 to 3? Can 0 to 3 in S ever equal to 0 to 3 in T? No, but like the part that's tripping me out is when we start shuffling 0 to 3, the indices in 0 to 3 start to shift a bit. Like, this is not constant. This is the part that I was thinking it's like what are we gonna cache because 0 to 3 is gonna change. What's the base case? Like the base case is when SL equals when SL equals to SR. When because when we get to like a single in when we get to a single, yeah. Okay, I get how we'll implement that, but I just don't get why it worked. But let's just implement it. If SL equal to SR, let's just go SL. T left, TR. If the left is equal to right, because these are indices, then we return. But we're gonna have to pass in like S and T as well. Yeah, that makes sense. S. Base case. Like the brute force is choose every midpoint. So choose every midpoint, SL to SR essentially, but we need to make sure it's non-empty as well. So for like GRE. So 0, 2, 3. We're gonna want to split at here. So for I and from S and L, so if we have a 0, we're gonna want to have 0. Right. S and T. We're gonna go SL. What's the mid? To SL plus mid. If mid is 0. Okay. Something like that. Did you use like the cache thing? Like the LRU cache? To mid. TL. TL plus mid. The right is keep the SL plus mid to SR. TR plus mid. Something like that. Because if or no, we just do mid. We start at mid. Plus 1. So SL. Do we even need SL and SR, or we just straight up need just one index? Or we just need the in. It might be redundant. We just need like left and right. This is literally keep as is. How do I swap though? Mid. Oh, I see. Let me think about this. So I'm trying to. I'm trying to make S the same as T. So at one point, I'm going to keep S as is. Okay, what does the swap mean? Okay, we have the left and right. Or here, let me just even remove this. Suppose we have 0 to 1 is the left. Right equals 1 to 2. Then what we're going to want to do is, if we want to swap it, we're going to want to compare left with the right. So we're going to have to try to throw left in and compare it with the right. So what's the left part? SL is pretty much like SL to mid. What's the right part? Is pretty much equals to mid to SR. So I want to take the left part. I can pass the left part and I can take the left part and pass it in with the left part, or I can take the left part and pass it in with the right part. So I'll compare my left to mid, or mid plus 1 to TR. Yo, chat, I actually don't know how to solve this. I don't know how to do the comparison thing, like flip them. Oh, you sent it? Let me fix the community moderation. Okay, I like fixed it so people could actually put links. Can you send it again? I changed it so people could put links. Okay, well. Yeah, it might show up for the next stream. I'll fix that. This is Alpha's code. Guys, appreciate you. Let me see. Yo, LeetCode has an app now. I don't get this reverse part. So you're comparing this middle to this middle. Or you're taking SL plus I, SR. Yeah, this is, I get this case. Okay, what's the reverse case? You're gonna take SR. Yo, the agent's tweaking out. Look at that. Facts. SR. So what's SR tell us? The right? Oh, this thing didn't even see. What reverse means here. You split a substring and swap the two parts. The right part of S must match the left part of T and vice versa. Yeah. For swap to work, S is right part, which is BC. Okay. Okay, this is the back part. Okay, and then we keep this the same. The TL. Damn. Yeah, this question cooked me. All right. I have to do some homework, which is some segment tree stuff that Ishan taught me. I need to sit down on this question a little bit longer. Google's actually asking this one? Bro, this is a brutal Google question if they're actually asking this on interviews. I might go live later where I'm dog fooding jamesperalta.com, so I might do. I need to finish my YC application. Oh my god. Okay, what do we do? Man, applying to the more I researched it, chat, I don't I think going into trying to do a VC route is not a good way to get rich. Even I was asking ChatGPT and it's just saying, bro, like that's a very risky path trying to start a company. Like my current path of just having a high salary, working at regular companies. Got chain analysis interview tomorrow. So I'm gonna do some homework. Apply to YC. Need to finish up my Europe trip stuff. What else am I gonna do? Segment tree practice. And then this DP question. And maybe 1 hour dog fooding. Dog fooding. Peralta.com. I have to dog food my own. Yeah, I actually came up with some of those ideas that y'all came up with in the chat were actually good. Yo, you got this. What does this company do? You already know what they're gonna ask you? Yo, let's see the salary. Do they even have engineering role? What role are you gonna be doing? Where is this? Where is this company located? Oh, look, getting a call. Give me a second. Where is this place? Man, good luck, man. Good luck. Denmark, good luck, man. Good luck. All right, everyone. Thanks for tuning in. Good luck on your interviews. I hope you learned something. Ishan, thanks as always for helping me out. Same with Alpha. Alpha, we need to do a coaching session. Help me out on some stuff too. I need to get coached by the top lead coders and see what that does for me. But all right, everyone. Thanks for tuning in. Catch y'all on the next video or stream. Peace.
This is not my main thing, really I'm a coder. Coffee stains and name chains, I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over. LeetCode, beast mode, 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 LeetCode, beast mode. This is not my main thing, really I'm a coder. Coffee stains and name chains, I am such a loner. San Francisco bases got me slowly taking over. I can't wait to show you that I'm gonna take it over.